So why don't we start to do some simulations and, see what's going on inside this model, try to understand the concepts of, what does neglected heterogeneity means, or what is the effect on state dependence, what if we fails to control for the initial conditions, what are the results going to be. And I apologize, so I'm written up here again the model. This is basically the equations that's kind of mimicking the simulation module that we had, basically this simulation module we have in the code, or the simulator here. And so the reason why I'm using this slightly different notation is because, I wrote the code first, and then I used all these letters, and then I realized that Woolrich, he was using other letters for say, I think he was like using phi instead of phi, and so there's a little bit of mix up between the notation above and then this notation, and I really apologize for yet another unforgivable zigzag and abuse of notation here. Okay, so this is just but this is a model. So we have a delta, which is the one coefficient of interest, and rho, which is another coefficient of interest, which is measuring the state dependence. This is measuring the effect of the state of the strict exogenous regressors. And then at the same time, we want to take control for CI. Okay. And so here in this model, I'm not allowing for any dependence in the simulation for any dependence of set. So set is not entering here, like we had set being set being in here. Okay, so we are kind of extracting for that when we are generating data that could be correlation between the other explanatory variables and the unobserved effect. Okay, but once we come to the empirical example I'm going to show you later, I'm going to try to control for it in that case. But here for the simulation exercise, I don't just want to keep it simple and only try to control for C and then the initial conditions, so that parameter phi y0 is here. Okay, so if this is positive, then you have a correlation between CI and yi0. Okay, and so if this parameter down here is positive, well, then you have unobserved heterogeneity. Okay, so now let's make some experiments with this model, okay, with dynamic models, and we're going to make a bunch of different experiments, and we're going to start with these questions first. So if we neglect heterogeneity in initial conditions, does pooled OLS and appropriate consistently estimate the average partial effect on the Lac dependent variable? Okay, or do we get spurious state dependence, like I kind of alluded to? What about the other parameters? What about the coefficient on the strict exogenous variables? Can we estimate those by pooled OLS and appropriate? What about if we try to account for that heterogeneity? Like, for instance, would it be valid to do a linear probability fixed effects model? Well, that's kind of derived under the strict exogeneity assumption. So maybe not so good if you have a Lac dependent variable, right? Anyway, we're going to look at it, see what the simulation tells us. Okay, one thing is theory. We will want to, use the computer as well. And then, can the random effects appropriate model approximate the average partial effect of the Lac dependent variable? And do we get? Can we identify that true state dependence? And what happens with those coefficients if we have correlation that between X and C? Now, the last question I'm going to defer to a little bit later because that's not in the model, right? So we're going to look at that in the empirical example towards the end, okay? But for now, let's just do some simulations. Okay. Now, so what I've done here is I've cranked up the simulation module again, simulated 5,000 observations, cross-sectional observations over 10 time periods. We're working with simulating data from the probit, and then the parameters from the specification above. The coefficient to the strict exogenous variable set, that's 1. And let's just start with the simplest possible case first. Let's put all the other parameters to 0, okay? So now we're in a world where we really have a strictly exogenous strictly exogenous regressor only in the data generating process. And we're going to try to estimate this with 4 different estimators. First with OLS, then with a pool probit, then with a fixed effect, and then with a random effects probit. Okay, we're going to vary the different coefficients in the different situations. It doesn't make sense to include, say, time constant variables when you do a fixed effects, for instance. Okay, but otherwise, the parameter, the variables we include is going to be basically the same in all of them. I'm going to just move away from the slideshow to see what's going on. Let's update this and see what we get. Okay, now the coefficient on set, well, this is the partial effect on of that strict exogenous variable, 0.28. And under these assumptions where you don't have any unobserved heterogeneity or lac dependent variable, well, I guess it should, we have seen before, it should approximate well the average partial effect. And it's also very close to that average partial effect you get from the probit model. Okay, and also you look at the coefficient. This coefficient is supposed to be P1. This is delta, the coefficient on set, and it is, okay, because there's no unobserved heterogeneity. So pool probit, that's actually maximum likelihood. Okay, and then the lac dependent variable coefficient, well, that's supposed to be 0. It's insignificant, just like it's insignificant here. Okay, initial conditions doesn't matter because I put phi equal to 0 in the data generating process. And so it's also insignificant like it's supposed to be. So everything here is just like we expected. Also in the linear fixed effects model, we get approximately the same as we get for the pooled OLS regression. These are both consistent under this data generating process because we have no correlation between the unobserved effect and the experimental variables. So everything seems nice so far. Let's look at the last one. This is the random effects probit model where we have controlled for the we're trying to estimate the effect of set and the lac dependent variable y. We put in a constant and control for initial conditions, and then we estimate this additional parameter, the variance on the unobserved effect. Well, we put that equal to 0 up here, so there's no unobserved heterogeneity in the data. So it's reassuring that we estimate it to be insignificant. Okay, and all these coefficients that's supposed to be 0 is insignificant. We estimate delta equal to 1, get an average partial effect that's completely in line with everything else. So far, so good. Okay, this is kind of the boring situation, right? Because it's not really a dynamic model, right? But let's put on step by step and see what happens with all these different estimators. See, the first thing I'm going to do is I'm not going to change rho. I'm going to try to simulate data from a static model and then estimate dynamic models and see if it can, if we can reject the hypothesis that this is actually equal to 0. Okay. But then I'm going to add some unobserved heterogeneity. Okay. So here it is, our unobserved heterogeneity. So now what you see is still that in the situation with unobserved heterogeneity, well, we still have the situation where we have that the coefficient on the sets are pretty much aligned across the different specifications. Okay, so the average partial effect, well, they kind of add up. Okay, that's kind of good to know, and theoretically this should be the case as well. Let's move on to the lac dependent variable, which is now our object of interest since we're looking at dynamic models. And look at this. It's suddenly you get an average partial coefficient in your pooled OLS regression of 0.4. Okay, what does this number mean? It means that if you take the example of the labor force participation, then if I was in the labor market last period, I have 41% higher chance to be in the labor market next period compared to a person who was not in the labor market. So this is a large effect. Okay, but see, the issue here is the rho is actually equal to 0. So this is not a causal effect. It's not because of me experiencing the event of being employed that I'm more likely to be employed next period. It's because of something else. It's because of the unobserved heterogeneity, right? This is the only thing we added, right? So that lac dependent variable, which is kind of, supposed to capture the persistence in the choices, how little those changes over time. That's capturing something else. It's capturing, well, it's capturing that persistence, but it's due to not state dependence, but due to unobserved heterogeneity. Let's look at the other estimators, see if they're doing better. Well, probet get exactly the same close coefficients that are close, right? Way too big, definitely not zero. Okay, well, we don't have the standard errors on the average partial effect. Then you need to do like bootstrapping or some kind of advanced delta method. Okay, so we don't have those, but we have the standard errors on the coefficients, and this is supposed to be zero, right? That's what it is under the data generating process, but it's highly significant. Okay, so again, this is not looking good for pull probet. Okay, and what about, what if we try to difference that unobserved heterogeneity away, right? Then it's not there anymore. Okay, and we're supposed to have be able to see that there's no state dependence. Well, it's actually not the case. Actually, it's now you got negative state dependence, a very significant negative state dependence. So what is going on here? Well, recall the linear fixed effects estimator was derived under the assumption we have that we have strict exogeneity, and the Lac dependent variable is not a strictly exogenous regressor, so that's not valid. It's not going to produce consistent estimates. It's going to produce inconsistent estimates. Okay, and see here we got something that's totally out of the realm. Okay, it's not. It's highly significant and wrong. So see, the problem is that basically the fixed effects estimation is trying to move away all persistent by assuming everything is time constant, but that persistent that is due to any unobserved effect is not time constant, right? So it's probably removing too much persistence. Okay. Anyway, you shouldn't really count on this, and I guess the bottom line here is don't use linear fixed effects regressions for dynamic models. Okay, it's not valid. If you want to do a linear fixed effects, or if you want to do a linear panel data model for a linear probability model, well, then you need to do the Arellano and Bond, or the IV approach, where you formulate the model in first differences, and then you appropriately instrument the Lac differences by further Lacs. Okay, to get rid of that endogeneity problem. Okay. We talked about that, or Jesper talked about that in his treatment of unobserved effects models, or linear panel data models. Okay, so what about the random effects probet? What is that? How is that doing? Well, okay, it's doing good. Got delta right. This is insignificant. Oh, it's kind of borderline significant. Okay, it's borderline significant. Well, what can you do? Maybe we didn't get this. It's exactly right. Well, it's very close to zero. Or it's very close to the true value 2. So we generated with a standard deviation of 2. So it's nailing that. The initial conditions, well, they were insignificant as should be, and so with a constant. Okay. Did I use robust standard errors of the sandwich formula here? I actually shouldn't. I should use A inverse, and maybe because in principle this is maximum likelihood. We don't even need that, right? So let's see. Maybe that would actually make it more. Well, it's insignificant. Okay, so I mean. Well, sometimes it is random data, so let's put it back to sandwich, but it is randomly generated data, and in 95% of the times we're gonna or 5% of the times, because we're testing at 5% significance level, we're going to be making wrong inference, right? What did I do here? It's a small s. Okay, so let's move on and try to make it a dynamic model. Okay, so see, can we estimate that coefficient right? Okay, and so I mean, the bottom line from what we just talked about before was, if you're not appropriately accounting for the unobserved heterogeneity by using the random effects model, well, then you're going to be in trouble. You're going to get spurious state dependence. You can't use the linear fixed effects model because it's assuming strict exogeneity. So that's kind of the bottom line from that exercise. So now we generated data from a dynamic model, and well, it is significant. The coefficient is positive as it's expected, right? So now it's a big effect. But remember, the part of this effect is due to that unobserved heterogeneity. Let's go down to the bottom and see if we got it right from a random effects model. Well, we did. It was these two coefficients supposed to be 1, and the average partial effect, what is that? 0.15. So this is like this is the good estimate of the true state dependence. Okay, essentially this model this is the type of model that generated the data. Okay, so let's see if we can find 0.15s in the other estimators. Definitely not here, it's too low. Definitely not here, it's way too big. I mean, it's like 3 times as big. Okay, and even bigger for the linear panel data model. So that's for the pooled OLS regression. So okay, so I think here the bottom line here is it's really important to appropriately control for the unobserved heterogeneity. Let's do another one here where we just simply let's not worry about this unobserved heterogeneity at all. Okay, and see if we can and then see if we can generate the same problems by having correlation with the unobserved effect, right? And see this, if there's no unobserved heterogeneity, but we have this correlation here, what about these, right? Well, we still get now again. No, let's put this to 0 here. Okay, so there's no true state dependence in the generated in the data, but yet we need this, of course. Okay, we need unobserved heterogeneity. Otherwise, it doesn't matter that it's correlated with initial conditions. Okay, yeah. So this is the exercise here. Okay, so now you again you get a significant state dependence, even the case where it's not supposed to be any, right? That's because of the initial conditions problem. Okay, and you do a pull probit, well, you get the same. You get a high average partial effect, and it's supposed to be 0. Okay, again here doesn't help to do fixed effects because we are relying on strict exogeneity, but here it nails it. We can reject that there is any state dependence based on a simple t-test. The t value is less than 2. So, and the average partial effect is really close to 0. Okay, so this is I think the bottom line here is, I think I kind of showed it in many different examples, that controlling for unobserved heterogeneity and individual fixed effects is extremely important. Okay, when you're estimating dynamic models. So here's some remarks. And I'm going to leave it here just in the interest of time. It's kind of just summarizing what we've just been through. Never mind. Yeah, so pool OLS is just heavily overestimates the average partial effect on Lac dependent variable when you have C present, because it's fewer state dependence, but it does provide good approximations of ZIT and the average partial effect on that. Okay. Basically, in none of the cases the linear probability model, there's a typo here, LPM, fixed effects is not appropriate for dynamic models. So because of the strict exogeneity is violated. Okay, but sometimes still approximate the average partial effect well. Okay, if C is uncorrelated with Y not. Okay, so in the trivial cases where strict exogeneity applies. Okay, accounting for unobserved heterogeneity is really important, and the random effects model does everything right. Okay, so here we are not allowing for any correlation between the unobserved between the unobserved heterogeneity and explanatory variables, the strict exogenous explanatory variable set, but we can easily do that. Okay, and we're going to look at actually how that makes a difference in an empirical example. If we want to allow for an arbitrary correlation between that, well, then you want to do the Honoré and Curie residue, but then we use identification of the average partial effects. Okay, so I'm going to stop here and then make us ready for the next video, which is about the empirical application in Woolridge's textbook in the example in table 15.3 and an example from about the dynamic model, but that's kind of after a short break. So see you soon. Bye bye.